Hello there, welcome to my channel on chemistry lessons. Predominantly it focuses on AQA A-level, but it also covers the BTEC applied science specification as well. Most of the videos at the moment do focus on full lesson content, but my aim is as we progress and grow that we'll end up with some shorter, sharp revision videos as well. Please subscribe, let me know what you think. Make sure you don't miss out on any of those future videos. Good luck. So this video is the second in a series of two, and it's an AQA A-level chemistry video. It's the A2, so second year topic on polymers, towards the back end of your organic stuff. Okay, so lesson one focused on condensation, polymerisation, and it also did a little bit of recap on your addition polymers from first year and GCSE. So this one here it's just the very end of this topic. It's looking at the disposal of polymers and the biodegradability. It's fairly short, okay, but it does draw upon your knowledge from the hydrolysis of esters stuff. So if you've got your hydrolysis of esters off down to a T, where you looked at the acid hydrolysis and base hydrolysis of esters, then this is an absolute doddle, okay? Otherwise, it's worth going and having a little bit of a recap on your hydrolysis of esters. So we'll start there then. We'll have a look at what we remember from our hydrolysis of esters. So let me just draw an ester link on the board. So there's our ester link, just whatever, R1, R2, and that's your ester link there. Now, hydrolysis is the breaking down using water. That's what it means, the breaking down using water. But we would speed this up by having an acid or a base present. Okay, so what we're doing is we add water across, we break the ester link, and you end up with the OH from water and the H from water. So you end back up, you break it down, and you end up with your alcohol and your carboxylic ester. So it's the reverse reaction of that esterification process. And if you recall, that process was in fact reversible. Okay, that was in fact a reversible reaction. Now, just one thing to remind you to look out for. If it's acid hydrolysis, then these are your two products. But if it was base hydrolysis, your acid would in fact also react with that base, and you would end up with your salt, whatever it was. If it was sodium hydroxide, you'd end up with your sodium salt, or potassium salt, whatever your hydroxide was, or your alkali was. Right then, let's remind ourselves of the structure of our three polymers that we've looked at. So polyester was a dicarboxylic acid joined to a diol, and the diol, and that would just repeat end on end. So that was the repeat unit of a polyester. And again, if you saw video one, what's in the middle here can vary, and that's what makes the polymers different. And polyamide, very similar, and instead of being a diol, it was a diamine. So we have an NH here. That was the only difference. And then we did look at the intermolecular forces here. We said that the intermolecular forces in polyester was dipole-dipole due to that carbonyl being a polar bond, and your intermolecular forces with your polyamide was hydrogen bonding because of the NH. And the third type of polymer was just your addition polymer, where you had carbons in the backbone like this, and then you just had your four groups here. I'll stick with the shapes I'm throwing here, throwing some shapes. There we go. So that's your addition polymers at the bottom, which is your alkenes and polyalkenes, and the top two, you got your polyester at the top and your polyamide in the middle. Now, in terms of the biodegradability, we already know that this ester link can be hydrolyzed using water, and it will do so under acidic conditions, basic conditions, or over a long period of time, because the reaction is slow, which is why we would use the acid or the base. But over a long period of time, it would occur naturally as long as water was present, and that would happen. And you get the same hydrolysis in a polyamide. So those ester and amide links will break down over time. However, the backbone of an addition polymer only contains carbon-carbon bonds, which will not hydrolyze. So addition polymers, your polyalkenes, are non-biodegradable. They will not break down, okay, because they are chemically inert, this carbon-carbon double bond. And that's your first bullet point there, look. Polyalkenes are chemically inert and non-biodegradable. Polyesters and polyamides can be broken down, and that's because of that link can be broken there, okay? And we've seen the products of that. It's just the reverse. They will break down back to their diamine or diol and dicarboxylic acid. Right, let's focus on the last point now then, which is advantages and disadvantages of different methods of disposal of polymers. Now, think about plastics, because plastics are polymers. That's what they are. So plastics are types of polymers. Now, it's big news at the moment in terms of plastic waste. So there's three main ways we can get rid of plastic. We can just use landfill. So we'll talk about each of these in a moment. There's landfill, incineration, and then there's recycle. Okay, now everyone's attention usually is drawn to recycle and say, oh, well, let's just recycle things, but it's not always that simple. So what we need to do is look at the pros and the cons for each type, each method, okay? I think this has covered an awful lot of GCSE and there's no different here, okay? I suggest that maybe you pause the video and have a little brainstorm yourself and see if you come up with the same things that we're going to discuss. So positives for landfill is it's really easy. It is exactly as it sounds. You tip it into a hole, you just dump it on the ground and then you cover it up when it's full. So it's really straightforward, really simple. However, negatives, it can release some toxic gases and obviously you can run out of space, so it requires a lot of space. Incineration, very similar to landfill, I guess, apart from we just burn it. So it's really simple, it's really straightforward. Again, advantages. Disadvantages though is, again, particularly with plastics, if you burn them, they do release some toxic fumes. Okay, so burning plastic is not good. Recycling does seem like a very good idea because you don't have those negatives of gases, etc. However, it is very difficult to actually, because once those plastics have been made, because generally a plastic is made for a specific purpose, and once it's been made for that purpose, it's very difficult to use it for something else, okay, or to remold it, or to to reuse that plastic. So it's not that straightforward. It does need very careful filtering and selecting and sorting out, which is very, very costly and time consuming. Right, your chance to have a go at some questions then. So what I suggest you do is I suggest you pause the video and have a go at these two, and when you're ready, unpause the video. Right, okay, question number one. The structure of a polyester chain is shown below. So let's have a look at this polymer. So they've drawn it quite awkward on purpose, but there's an ester link, there's an ester link. So already we can identify the dicarboxylic acid in the diol. But let's read the question. Which statement correctly explains why plastics are made from polyester are often softened at high temperatures? Okay, is it because of hydrogen bonds and van der Waals forces? Well, there won't be any hydrogen bonds between any of these, so it's not that one. I'm eliminating it. Permanent dipole and van der Waals. That sounds to me like the correct answer, but let's make sure that C and D are wrong, because we would have permanent dipoles from the carbonyl groups and would also have van der Waals because they exist between all molecules. Carbon-carbon bonds in the chain is wrong. Well, that's true. So that statement is true, but it doesn't explain why the polymer will soften at high temperatures. The polymer softens when the chains can move along or move past each other. So I'm saying that C's, although the statement's correct, it's not the reason for softening. Carbon-oxygen bonds are strong. Well, actually, those are the bonds that hydrolyze, so I wouldn't say they are that strong. So actually, I'm getting rid of that one. The answer is B. I like the way I've given myself 2 marks there. Makes yourself feel better, give yourself 2 ticks. Right, which polymer is least likely to be biodegraded after several years in landfill site? Now, we know that polyesters, polyamides can biodegrade over a long period of time, but polyalkenes can't, so addition polymers can't. Now, Kevlar, nylon and terylene, they were our 3 specific examples of polyesters and polyamides. Polythene, that's an addition polymer. That's the only one. That's not going to break down because of its strong carbon-carbon backbone. Kevlar, nylon, terylene will all have some either amide links or ester links in them, so they will biodegrade. The answer for this is C. Okay, question 3 then. So pause the video, have got the question, and when you're ready, unpause the video. Okay, so we're asked in A to draw the structure of the monomer from polymer P. Well, polymer P is a polyalkene, it's an addition polymer, therefore the monomer will look something like this. Now I just need to identify the 4 groups. So we've got CH3 up here, Cl down here, CH3 and a H. And the type of polymerisation is addition polymerisation. 1 mark for the monomer, 1 mark for addition. And polymer Q, this is a polyester. So let's break the ester links. There they are. And we should identify that we've got a diol. So structure of compound 1 is going to be HO, then it's a C, C, OH. So there's our diol. We had a H at the top there, and a H here. And then we've got CH3, CH3. So that's one of the monomers. The other monomer is going to be dicarboxylic acid. So all I'm doing now is identifying my 2 carbonyls. Those 2 carbonyls become carboxylic acids. There we are there. So there's my 2 carboxylic acids. And make sure I've got the correct structure for the bit in the middle. That's a CH2, and this one has 2 CH3 groups attached to it. Again, 1 mark for each structure. And this is the main aim of today, was to look at the environmental advantages and the biodegradability and disposal of polymers. So what advantage does Q have over polymer P? Well, polymer Q will biodegrade, polymer P won't. The reason being, the justification, we can go down 2 angles here. So the justification is polymer P only has strong carbon-carbon bonds, which will not break, so it won't break down. Whereas the polyester, the main thing, and I don't think I made it very clear actually in my explanation, but what happens here is, because you've got that carbonyl, so this is your carbonyl chemistry, that carbonyl is delta plus. It's susceptible to attack. It will attract nucleophiles, and that's what happens when this bond breaks down. So it will attack and attract nucleophiles. This bond will break. So the justification is, due to the polarity or the polar carbonyl bond, the ester link is susceptible to breakage and it will break down over time. It can be attacked by nucleophiles, whereas the strong carbon-carbon backbone of your polyalkene cannot. Okay, so next questions to look at then. 7 marks up for grabs here. So pause the video, and when you've had a go, unpause it and we'll go through it. Okay, so B is mostly from the previous lesson, but it's definitely worth obviously continuing to practice as much as we can. So we want a polyamide, so we've got the 2 monomers. So here we've got an NH, so this has got 4 CH2s, 1, 2, 3, 4. There we go. I could obviously put this in brackets if I wanted to and just put CH2, 4, but I'm going to draw the full thing out. So there's my diamide, or my diamine. There's the square brackets at one end, and it's hexane dioic acid. So it's going to be dioic acid, 6 carbons. Now be careful, it's not going to be 6 carbons in between, there's only going to be 4 carbons in between, because the hexane dioic acid, the carbons within the carboxylic acid group will be carbons 1 and 6. So 1, 2, 3, 4, 5, 6, and then there we go, final amide link at the end. So there's my 2. That's a repeating structure. That's going to be worth 2 marks. And then it says discuss the interactions between chains of polyamides. Well, they'll be van der Waals, but the main or the strongest intermolecular force is going to be hydrogen bonding due to that NH polar bond. Okay, so the idea that it's got the NH polar bond, which will allow it to show hydrogen bonding between polymer chains. So there's one mark for identifying hydrogen bonds and the second mark for explaining. Okay, so there's my 4 marks. And now part C. Why polyamides are degraded by sodium hydroxide, whereas polymers such as polythene are not. So we're seeing that this is starting to repeat a little bit on us now. So the idea that polythene only has carbon bonds in the chain or in the backbone, and therefore is not susceptible to attack by hydroxide nucleophiles or by nucleophiles for that matter, so it won't degrade. However, the polyamide can be attacked by hydroxide nucleophiles. So here, hydroxide nucleophiles can attack this delta plus carbonyl group, and that's what causes the breakdown or the hydrolysis. Okay. Next question then. So 6 marks of the graphs here. You know what to do. Pause the video, and when you're ready, unpause the video and we'll go through it. So we should start to see quite a repeat happening here, because again we're being asked to compare polyalkene with either a polyamide or a polyester, but it's always going to be the same response, the same answer. So here, an experiment we could heat them both with sodium hydroxide, and the polyalkene we would see no reaction taking place. The polyamide we would see a reaction. It would be hydrolyzed, it would be broken down, and you could, even if you wanted to, go on to identify what you would see. So if we'd broken it down with sodium hydroxide, for example, we would expect to see salts of the acid. So the dicarboxylic acid, whatever that is, we would form salts of the acid. Don't really need that for your 3 marks though. You can just say heat them both with sodium hydroxide, no reaction with the polyalkene, and the polyamide would hydrolyze. That's enough for your 3 marks. So part 2, an advantages or a disadvantages of a different method of disposal. So this is quite an open question really. So we could talk about either recycling, and if we talked about recycling, we could say the advantage would be that we don't use up valuable space. We could talk about a disadvantage of recycling and say that the plastics would require to be sorted, which is very time consuming and can be expensive. Or we could talk about another type of disposal, which is incineration, and we could say that incineration advantage is that it releases energy, because you could burn these things to release energy. Or a disadvantage could be that incineration produces toxic fumes. So you've got it's quite an open-ended question, that one. You've got quite a few different responses. And that brings this video to a close. So hopefully these have proven useful. Again, you know what to do. Subscribe so you don't miss out on future videos. I am planning, people have asked me several times, I'm planning on going back and covering the early year 2 topics. I will do that as soon as I get a chance. But again, please keep the comments coming. Let me know what you want, and good luck.